Welcome to Math with Professor V. In this video, we're going to be solving my most recent exam that I gave to my Calculus 2 students. So I asked them, would you like a video recording the solutions? They said, yes, Professor V. And I figured it would benefit not just them, but everybody else out there who might be reviewing or prepping for Calc 2. Now, at the college I teach at, we include solids of revolution, and work problems and average rate of change in Calc 2. I know a lot of schools have those topics in Calculus 1. So if you're a little confused by the topic order, that's why. Also, we use an early transcendentals textbook. If you use late at your school, then some topics are going to be a little different, okay? But here we go. Evaluate the integral. This is actually, I put some review stuff on there just involving u substitution because it's so crucial and important. So here we have an indefinite integral of 1 plus x over 1 plus x squared dx. Now what you need to do is split this into two integrals actually, and then tackle them separately. So we have 1 over 1 plus x squared dx plus, and then here just x over 1 plus x squared dx. So let's talk about what each of them is going to result in. So the first one, hopefully you recognize, boop, that's tan inverse of x. That's the antiderivative, or arctan of x, same thing. So I'll just call this tan inverse of x plus c1 for that first integral. Now the second one's going to take a little bit more work. Notice here I have 1 plus x squared in the denominator, and then I have x to the first in the numerator. So let's do a u substitution. Anytime you have 1 degree lower up top, and it's just one little term, that's usually going to work out nicely. So let's let u equal 1 plus x squared, and then du would be 2x dx. So what do I have exactly in the numerator? It's x dx. So that means 1/2 du is x dx, and then we can rewrite this integral now. We can rewrite it as, let's put the 1/2 outside, x dx is just du over u. Very nice. So antiderivative, this is just 1 over u. Do you know what it is? Oh good, natural log, absolute value of u. And I'm going to put plus c2 because I have a constant from this second little integral that I'm doing. And then don't forget we have to go back, replace u, oops, I want a highlighter, replace u with the original variable 1 plus x squared. And 1 plus x squared is never negative, so I don't need to keep writing absolute value bars. If you want to drop them, feel free. So this is 1/2 natural log 1 plus x squared plus c2. So all together, I'm gonna just add everybody up from each of the two little separate integrals. So we have tan inverse of x plus 1/2 natural log 1 plus x squared plus c. Then tell the people, who is c? c equals c1 plus c2. And that's it. That's problem 1A. Just good old u substitution. So that's a review topic. We did go over it again though, the first week of the semester, because when you're learning all these new integration techniques, you can't forget the bread and butter, the basics, u substitution. Okay, another u sub. Yes, indeed. This time with a definite integral from 1 to 2 e to the 1 over x dx over x squared. So in this case, we're going to go ahead and let u be 1 over x, which you'll remember is x to the negative first. So if I take the derivative of both sides, du is going to be negative x to the negative second dx, which is negative 1 over x squared dx. Do you see how we have that in our integral? Here's 1 over x squared dx. But let me just move the negative to the other side. So negative du is 1 over x squared dx. And then we also need to change the limits of integration right away. 1 and 2 belong to the variable x. So I need to figure out what they are in terms of u. So you're just going to come right here and substitute them in for x. So u of 1, that's 1 over 1, still 1. And then u of 2 is 1/2. Okay, so now let's rewrite our integral. Lower limit stays 1. New upper limit is 1/2. E to the 1 over x becomes e to the u. And then dx over x squared, all of this is just negative du. So let's put the negative outside, du right here. Very nice. Is something screaming at you? Because something's jumping out at me. Let's get rid of the negative and flip our limits of integration. So let's go 1/2 to 1, and then now we have positive e to the u du. Oh, I love it so much better already. You know the antiderivative of e to the u? It's one of my favorites. E to the u. And then we're going to evaluate from 1/2 to 1. Okay, no, don't go back to the original variable this time because we switched our limits. They're in terms of u. Everything's matchy-matchy. Just go from here. So this is going to be e to the first minus e to the 1/2. Leave answers in exact form. So just e minus, that's square root of e. And that's as cleaned up as things get. Okay? Very good. So those were review problems, but very crucial. So that's done. Next, area between curves. So find the area enclosed by the given curves. You must include a neatly labeled sketch of the curves and region. So we have here parabola, y equals 2x minus x squared, and then y equals 2x minus 4. Absolutely, the first thing you always need to do is find the intersection of these two curves. The intersection is essential for finding the graph properly, as well as knowing what your limits of integration should be for the area. So let's set 2x minus x squared equal to 2x minus 4. And then look how nice, the 2x's cancel, and then I have negative x squared equals negative 4. So x squared equals positive 4, x equals plus or minus 2. So let's see what each of the y coordinates would be. You can plug it into either equation. This one looks easier. So if x is positive 2, then y is going to be 2 times 2 minus 4, 0. And if x is negative 2, y is going to be negative 8. All right, very good. Another thing that can help you graph, like for this parabola here, y equals 2x minus x squared. If I factor out an x, I have 2 minus x. So I see that the x-intercepts for the parabola are 0, 0, and 2, 0. In case you forgot from pre-calc, the vertex of a parabola is always halfway between its x-intercepts. So if its x-intercepts are at 0 and 2, the vertex is going to be at 1 comma something. So 1, and then I mean, this is just to help us draw like the most beautiful graph possible. If I plug in 1, I'm going to have 2 times 1 minus 1, which is just 1. So with those 3 points, and I know where the intersection is, I'm in business. So let's get our graph going. We do have to go down to negative 8, but it doesn't look like we have to come up very high. Like we don't have to come up past 1, so I won't. And here's my x-axis, here's my y-axis. I'll say this is 1, this is 2, negative 1, negative 2. And then 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's start plotting all the points on the parabola. The parabola goes through 0, 0, 1, 1, 2, 0, and then it also intersects the line at negative 2, negative 8. That's here. You don't have to draw the full parabola, right? Just the portion that's going to be relevant for the problem. And then my line, 2x minus 4, well, I know it goes through 2, 0, and negative 2, negative 8. 1, 2, 3, 4. And its y-intercept is negative 4. So it should go through all 3 of these points here. Perfect. Okay, so I'll label again. This is 2x minus 4. And this is the parabola, 2x minus x squared. So the region enclosed by them, you can see it's all of this right here. And in order to find the area, we have to decide, should we integrate with respect to x or y? Well, the way the equations are given, it's already in terms of x. So I feel like it makes sense to integrate with respect to x. And sure enough, if I try to stack some rectangles, it makes the most sense to have the bases move in the x direction, and then the height we can determine by top function minus bottom function. So the base is delta x, which becomes dx in our integral. And then the height is going to be the function that bounds it on the top, which is 2x minus x squared, minus the function that bounds the region on the bottom, which is the line, 2x minus 4. All right, good. So the 2x's cancel. This ends up being negative x squared plus 4. So we're ready to set up our integral for the area. It's going to be definite integral. Now the limits of integration need to be with respect to x because we're integrating with respect to x. So look at the region here. It starts at x equals negative 2 and it goes all the way up until x equals positive 2. So those are our limits. And then I have base, which is going to become dx times height, negative x squared plus 4. Okay. Now one thing I want to make clear, a lot of the times it's tempting when you have limits of integration that are opposites of each other, evenly spaced about x equals 0, to cut it in half and just go 0 to 2 and double it. But you're not allowed to do that here because notice this region is not symmetric on both sides. So you can't just go 0 to 2 and double it. Okay, we don't have symmetry with respect to the y-axis. So you must keep things as they are, no shortcuts. Then we just start integrating. Negative x squared, that's going to be negative 1/3 x cubed, antiderivative of that guy, plus 4x, very good, from negative 2 to 2. And then let's plug everything in. So negative 1/3 times 2 cubed is 8, plus 4 times 8, 4 times 2 is 8. And then minus negative 1/3 times negative 2 cubed, and then plus 4 times negative 2, that's negative 8. So let's see, what do we have here? I have negative 8/3 plus 8. This is plus 8/3, but then now it becomes minus 8/3, and then plus another 8. So that's negative 16/3 plus 16. So that's 2/3 times 16, or 32/3. And that's it. Area between curves should never be negative, okay? So because it's just enclosed by two curves, it's not a net area with respect to the x-axis like you first learned. So if you get a negative number here, then you can catch a mistake, hopefully. You probably set your heights up backwards or something like that. All right, very good. Now we're moving on to solids of revolution. So find the volume of the solid obtained by rotating the region bounded by the given curves about a specified line. Sketch the region, the solid, and a typical disc or washer. I also was fine if students wanted to do the shell method instead. Very few did, but I can work it out both ways if you'd like to see. I did say disc or washer, but since, I let them live. If they want to do the shell method, have at it. So we have here y equals x cubed, y equals 0, x equals 1, all getting spun around x equals 2. I don't really need to solve for intersection here. I know what x cubed looks like, and I'm only going to graph it up till x equals 1. So I feel pretty comfortable just plotting right now. And then we're going to spin around x equals 2. So I'm going to give myself a lot of space in the positive x direction to allow for a nice graph. So here's x, here's y. Here's x is 1, x is 2, and then we're going to spin. So hold on. I'm going to graph x cubed. So it's going to go through 0, 0, and 1, 1. You don't really see much of what's going on, just this little baby sliver. It's cool. We love it. That's x cubed. Y equals 0 means the x-axis is also bounding the region. And then x equals 1 is also bounding the region. And we're spinning around x equals 2. We're spinning around this line. So first, can you correctly identify what region we're spinning? it has to be bounded by x cubed, y equals 0, and x equals 1. If you said this little region in here, you're correct. Okay, so first figure that out. Let me just plot this not so crazily. Okay, and then we're spinning it around x equals 2. So be careful. You see how there's this 1 unit gap around the axis of rotation? Match it on the other side. Reflect it properly. There's going to be a little gap. Come over here. And your solid's going to look something like this, okay? Good. Now, you have to decide what method you want to do. So like I said, most did, it's washers. There's a hole in the middle. So if you're going to use the washer method, remember, you're going to slice perpendicular to the axis of rotation. So if we're spinning around x equals 2, okay, slicing perpendicular means I'm taking slices that move up and down in the y direction. So if you're going to do washers, then you integrate with respect to y. So that means I need to rearrange my functions, and instead of thinking of this as y equals x cubed, I'm going to think of this as x equals cube root of y. Okay, so now let's go through, let's draw a typical washer. So there's the outer radius, and then this is the inner radius, okay? The outer radius, always look at the original region before you spun. So please don't look over here. You must look over here. Outer radius, big R, goes from axis of rotation to the outer edge, okay? To figure out big R, just look at what is bounding the outer radius on the right minus what's bounding it on the left. Just like with areas between curves, when you found heights, right minus left, we're doing the same thing here. Right minus left. Who is this? This is x equals 2. Who is this? This is x equals cube root of y. So outer radius is 2 minus cube root of y. I'll say that again. Big R, outer radius, go from the center to the outer edge. Always right minus left. You'll never do left minus right. You have to do bigger minus smaller, okay? Right minus left. Now, inner radius, let me switch colors so you can see it beautifully, okay? We won't be needing red today. Oh, certainly not. Inner radius goes from axis of rotation to that inner edge right there. That's little r. That's baby r. Who's bounding it on the right? X equals 2. Who's bounding it on the left? It's always x equals 1. So inner radius is 2 minus 1, which is 1. Okay, so let's set up our integral now. Volume is going to be, if we're doing washer method, you have pi r squared, big R squared minus little r squared. So pi times, limits have to be for y because we're integrating with respect to y. So 0 to 1. Big R squared, so 2 minus cube root of y squared minus little r squared, which is 1 dy. Okay, now we need to clean up. So this is pi times the integral 0 to 1. Remember, 2 minus cube root of y is 2 minus y to the 1/3. And then we're going to square it. So don't forget, you have that middle term when you FOIL. This is going to be 4 minus 4y to the 1/3. If you square y to the 1/3, you double the exponent. So it's going to be plus y to the 2/3 minus 1 dy. And then putting it all together, let's see, this is pi 0 to 1. 4 minus 1, I can combine those like terms. 3 minus 4y to the 1/3 plus y to the 2/3 dy. So here we have pi. Now we're ready to take the antiderivative. So 3 becomes 3y minus 4 times, add 1 to the exponent. 1/3 plus 1, we have y to the 4/3. Dividing by the new exponent means I multiply by the reciprocal, 3/4. Plus, y to the 2/3 becomes y to the 5/3, and you need a 3/5 in the front. Good thing we're just evaluating this from 0 to 1. Holy smokes. Okay, these 4's cancel. That's promising. Let's see what else happens. This is pi times 3 times 1 minus 3 times 1 plus 3/5 times 1. And then if I plug in 0, everybody's 0. Ooh, these cancel. This is lovely. And then I just have 3/5 times pi. So the answer is 3 pi over 5. Again, your volumes for solids of revolution should not be negative, okay? When you move on to Calc 3, you're going to do some like net volumes, or if it's below the XY plane, that's considered negative, but not in this class. All right, I did mention some people did shells. I had intended for them to do, the washer method, but whatever. I wasn't super clear, so I didn't really care. I'm just going to use the same picture. If someone chose to do the shell method, it actually came out nice. So here's the thing to remember. When you switch methods, you switch which variable you're integrating with respect to. So if washers meant we're going to integrate with respect to y, then if we're going to use cylindrical shells, that means we integrate with respect to x. And you peel parallel to the axis of revolution. So you need to draw a typical cylindrical shell. So the way to do that is if you're spinning around a vertical line, you draw a little baby vertical line segment in the original region, and that's the height of your cylindrical shell. That's the height of your cylinder. That's h. And then just reflect it on the other side, and then you draw a little typical shell. Okay. The radius is right here, and then we're going to figure out the height. So for the shell method, height is going to be top function minus bottom function. Top minus bottom. On the top is x cubed, y equals x cubed. On the bottom is y equals 0. So x cubed minus 0, just x cubed. Now the radius. The radius for shells is different than when you do discs and washers. You never use any of the functions here when you're giving the radius for shells. It's just going to be plain old x if you're integrating with respect to x, plain old y if you're integrating with respect to y, and then sometimes plus or minus a constant depending what you're spinning around. But don't get x cubed all up in the radius the way we did over here. Well, cube root of y, but you get what I'm saying? It's just going to be x or it's just going to be y. Why do I say that? Because the radius marks where you are in your little partitions along the x-axis when you're peeling each cylindrical shell. It does not have anything to do with the function. That is all controlled with the height of each shell, okay? So in this case, for the radius, just do right minus left again, okay? The rules aren't changing. Right minus left. Who is this on the right? X equals 2. Who is this on the left? Whatever x we decide to draw the shell at. So what I'm saying is, if you drew your shell right here instead, yes, up to here is whatever x value you decided to draw it at. And then here is some other x value that you're drawing it at. That's why we call each of them x. But in this case, we have right minus left, so the radius is 2 minus whatever x you're drawing it at. Okay, 2 minus x. That's because we're spinning around x equals 2. It shifts it. All right, so we have those two little pieces of info. I'm going to drag them down with me. Do you know what the limits of integration should be? They have to be, in terms of x, based on the original region before you spun. So the original region's only right here. So it should go x equals 0 to 1. Do not go 0 to 2. Then you would be adding in this piece, which it should be open. So don't do that. Original region before you spin, 0 to 1. I'm going to drag these down with me, okay? And then now let's set it up for shells. It's not bad. It actually ended up being like a cute little integral. So the volume's going to be 2 pi. Remember, shells has 2 pi outside, and then nothing gets squared. So 0 to 1, radius times height. So x cubed times 2 minus x dx. This is actually an easier integral, don't you think? 2 pi 0 to 1, now you distribute 2x cubed minus x to the 4th dx, just because there's no exponents that have fractions in them. Let's see. it'll become x to the fourth divided by 2. So that's 1/2 x to the fourth minus 1/5 x to the fifth from 0 to 1. So this is 2 pi times 1/2 times 1 minus 1/5 times 1 minus 0. 1/2 minus 1/5, that's 3/10, is it not? 2 pi times 3/10. Lo and behold, what did we get? The same result, 3 pi over 5. I love it. Beautiful. Okay, that's that. So some people did 2 problems with shells because the next one is a shell problem. Use the shell method to find the volume of the solid generated by revolving the region bounded by the given curves and lines about the axis. You must include a clearly labeled sketch of the region, the solid, and a typical shell. So I was nice. I said they've graphed enough already. I'm going to give them 1, but they just have to spin this region about the line y equals 1. So y equals 1 is right here. Spin it, so just kind of reflect it like this, and they need to draw a typical shell. So they need to use the shell method in this problem, okay? So if you spin around a horizontal line, go in the original region, draw yourself a baby horizontal line segment, and stay in the original region, please, okay? And I have to say, for the most part, oh my goodness, my students did such a good job. It's very common they, when they're first learning, they draw the shell too far into the open space. But oh my goodness, they practiced. They did a beautiful job. Okay, then you reflect that little line segment on the other side. That's the height. And then you just make yourself a little cylinder, okay? There's your shell. So this right here is the height. Very good. And then the radius, I'll do it in pink right here. There's the radius. Okay, so the height is going to be given by whatever function bounds it on the right minus left. So look here, on the right minus left, we have the solid curve minus the dashed curve. So solid is 6 cube root of y minus dashed curve 6y squared. What about the radius? Radius is going to be top minus bottom. On the top, I have y equals 1. On the bottom, it's just y. Remember, don't get the functions involved. So radius is 1 minus y. If you're struggling with solids of revolution, I have so many videos, so I'll link one of them here. I'll put them in the description too, okay? I know, these can be rough. Good. And then yes, if we're spinning around y equals 1 and I peel parallel to the axis of revolution, we're integrating with respect to y. So everything's perfect. The limits need to go just from 0 to 1. It's always based on the original region before you spun. So here we have v equals 2 pi, 0 to 1. And then radius times height. So we have 6 cube root of y minus 6y squared times 1 minus y dy. Now, one thing I'm noticing is I can factor out a 6 from both these terms. So let me move it outside. That way, when I FOIL, it's not so messy. So 12 pi times 0 to 1, and then this is y to the 1/3 minus y squared times 1 minus y dy. So we do need to multiply all this out, or we need to FOIL it all out, okay? So here we go, 12 pi. I still have my integral sign. I haven't taken any antiderivatives yet. So we'll have y to the 1/3 minus y to the 1/3 times y. You're going to add the exponents. That's y to the 1st. So it's going to become y to the 4/3. Inner term minus y squared. Last term is plus y cubed dy. Good. Let's keep it going. So this is 12 pi, antiderivative here, add 1 to the exponent, divide by the new exponent, 3/4 y to the 4/3. Let's see, minus, what's this going to become? Y to the 7/3, so 3/7 y to the 7/3 minus antiderivative of y squared is 1/3 y cubed, and then plus 1/4 y to the 4th. All of this from 0 to 1, thankfully. Okay, so then we have 12 pi times 3/4 minus 3/7 minus 1/3 plus 1/4 minus 0, right? Let's see, 3/4 plus a fourth, that's 1. So I have 1 minus a third minus 3/7 times 12 pi. Oops, that's my alarm. Little does it know, I've been up for hours. Okay, and then let's see, common denominator for these all is 21. So we have 12 pi times 1 is going to become 21 over 21 minus, this is 7 over 21 minus 9. So this is all over 21. And then that's 21 minus 16. So 5 over 21. 12 pi times 5 over 21. I can cancel out a 3, can't I? So this becomes a 7 and this becomes a 4. So final answer should be 20 pi over 7. And that's it. Okay, very good. I think those are some of the hardest sections, although surprisingly they did quite well. So that's good. All right, problem 5. Work problems, and this is with pumping fluids out of containers. I have an extra video on this topic. So the base of a rectangular tank measures 3 feet by 5 feet, and then the tank is 6 feet tall, and its top is 4 feet below ground level. The tank is full of water weighing 20 pounds per foot cubed. How much work does it take to empty the tank by pumping the water to ground level? Give an exact answer with appropriate units and include a label diagram representing the problem. So they told me the base measures 3 by 5 feet. So I'll say this is 3 feet, this is 5 feet, and then the tank is 6 feet tall. Plus there's like another 4 feet to get to ground level. So ground level's here, let's say, okay? And the water weighs 20 pounds per foot cubed. We're going to use that later in the problem. So they want to know how much work it takes to pump all of the water out of the tank. So what we're going to do is figure out how much force it takes to lift some arbitrary layer of water, multiply that by the distance that each arbitrary layer has to move to get out of the tank, and then add up all those layers, okay? And so the step-by-step process basically goes like this. You draw a typical layer. So I know you can't really slice water, so it sounds weird. You're like, what in the world are you talking about? But you just pretend like you can. Sorry, that's a wee bit crooked. But you have some little slice of water in this tank, okay? And it's got like a little thickness. So I want to compute the volume of this ith slice. So I'm going to call it V sub I. That's my first step. So we know volume. In this case, each little slice is a rectangle. So rectangles' volumes are length times width times height. So the length and the width are 3 and 5 feet respectively. And then the height is some little delta x. So I'm going to call down here x equals 0. And then all the way up at the top, this is x equals 6. And then the height of that little layer is just delta x, okay? You can also, in the past, I've called this y equals 0, y equals 6, because you know it's going up and down, but it doesn't make a difference. So height is always just going to be delta x or delta y. So this is 15 delta x, and then put units on it. So since it's volume and everything's in feet, this is feet cubed, okay? Now, I want the force required to lift the ith layer out of the pool. Okay, well, what are the units for force? Here we're in the imperial system. So the units of force are pounds. Okay, if we were working in metric, it would be newtons, okay? So we have to get pounds somehow. Well, this is where the weight density of water is important, because they told me water weighs 20 pounds per feet cubed. So F sub I, the force required to lift the ith layer, is going to be 20 pounds per foot cubed times the quantity that we just got earlier, this 15 delta x feet cubed. And this is where it is helpful if you keep the units going, because then look, you can see, oh yeah, feet cubed canceled. And what units am I left with now? I'm just left with pounds. Perfect. That represents a force. So then 20 times 15, that's going to be 300, keep the delta x, pounds. Okay, very good. Third step, what's the distance that each ice layer has to move to get out of the tank? Okay. So let's think about it this way. The layer that's at x equals 0, how far does it have to move to get all the way out of the tank? Not just out of the tank. Oh, heavens no. They said all the way to ground level. And remember, we have an extra 4 feet that were buried below ground. So the water all the way at x equals 0 has to go 10 feet to get to ground level. What about the one that's already at the top at 6? It has to go 4 feet. So it has to go a total of 10 minus whatever x sub I it's at. So it moves 10 minus x sub I, or just x. When we integrate, we drop the little subscripts, the i's, okay? So we're ready to put everything together now. Yes, so the work is going to be our integral. Now, you only include on your limits of integration where there's actual water that you need to lift. Why am I saying that? Because the water is only from 0 to 6 feet. There's no water here, right? So you're only slicing or lifting water from 0 to 6, not 0 to 10. 0 to 6, and then we have 10 minus x, that's the distance. Force is 300 delta x, which becomes dx in our integral. Okay? Very good. If I were you, I would take that 300 out immediately. And then we can integrate. This is going to be 10x minus 1/2 x squared from 0 to 6. And then we have 300 times, this is going to be 60 minus 1/2 times 36. Oops. Minus 0. So that's 60 minus 18. That's 42 times 300, which gives us 12,600. What are the units? It's foot pounds, okay? So in metric system, work is measured in joules. In imperial, it's foot pounds, okay? Good, or US customary system. Okay, whatever, there's so many names. That's that. Now moving on to average value. So A, find the average value of the function over the given interval. Part B says find C such that f of C equals the average value of the function on the interval. And then C, sketch the graph of f and a rectangle whose area is the same as the area under the graph of f. Label all relevant components that you found in parts A and B. Okay, so first you have to make sure you remember the formula for average value of a function. So f average equals 1 over b minus a times the integral from a to b of f of x dx. And a and b are given right there, 2 and 5. So this is 1 over 5 minus 2 times the integral from 2 to 5. F of x is x minus 3 squared dx. Okay, so this is going to be 1/3, and then most students were fine. You can u sub, let u equal x minus 3, but then du is just dx, so you don't even need to do it. Some foiled it out. Oh, I felt so sad for them, because you don't need to. Just add 1 to the exponent, divide by the new exponent, and then keep everybody so happy together like this. You see? X minus 3 cubed divided by 3. And then we're going to evaluate this from 2 to 5. 1/3 times 1/3 is 1/9. Keep that outside. And then I have 5 minus 3 cubed, so that's 2 cubed. minus 2 minus 3, that's negative 1 cubed. So what does this end up being? 8 plus 1, that's 9. 1/9 times 9 gives me 1. So that's the average value of the function on the interval. That means on average, the function values, the y values, are 1. Okay, very good. Part B, find C such that f of C equals that average value. So f of C has to equal whatever I found in part A, which was 1. I'm going to solve for C now. So f of x is x minus 3 squared. That means f of C is c minus 3 squared equals 1. Go ahead, let's take the square root of both sides. Don't forget you have to put plus or minus on the right-hand side when you do that. So then we have c minus 3 equals plus or minus 1. If I add 3, then I get c is either 1 plus 3, which is 4, or negative 1 plus 3, which is 2. And both those are good to go. They're on the interval from 2 to 5. Okay, very nice. Last thing says, sketch the graph of f and a rectangle whose area is the same as the area under the graph of f. Label all relevant components. So the rectangle, we're going to use the average value. That's going to tell me the height of the rectangle. That's the height of my rectangle. And the base of the rectangle is going to be determined by the interval that was given. So the base of the rectangle goes from 2 to 5. And then I'm just going to draw x minus 3 squared on that interval as well. Okay, so part C, I'm going to draw f of x equals x minus 3 squared, but only on the interval from 2 to 5. So let's see, if I plug in 2 for x, I'm going to get 1. That's not bad. What about if I plug in 5? I get 4. Oh, what a nice little graph then. And then you see how it's x minus 3 squared? That means the vertex of the parabola is at 3, 0. It's been shifted 3 units to the right. 1, 2, 3, 4, right here. So we said if x is 2, f of x is 1. If x is 5, f of x is 4. And the vertex is right here at 3, 0. Here's the parabola. I mean, we might as well draw 4, 1 while we're at it, right? Okay. So the area under the parabola from 2 to 5 is right here. And they want me to draw a rectangle that has the same area as this blue shaded region. Well, we just said a second ago, the base of the rectangle is going to go from 2 to 5, and the height of the rectangle is 1. That's why we found the average value. So the function on average has a height of 1, and the rectangle should have that height as well. And then that purple stripy area is equal to the blue shaded area, okay? And then if you'll notice here, when we found the values of c, that told me when the function was equal to the average value. So that tells you when the function, when the parabola should intersect the height of the rectangle. And look, it happens. They intersect right here at 2, and then they intersect again right here at 4. And that was what the c values were. All right, that's the end of that problem. Most people did great on it. Now for integration techniques. Here we go. Evaluate the integral. 7a, we have an indefinite integral of x squared minus 6x times e to the x dx. So this requires integration by parts. And I'm looking, I have a polynomial times an exponential function. So when you're choosing u, you always want it to be the polynomial. Because with each derivative, it'll get simpler. The degree goes down. Nothing happens with e to the x. It does not change as you keep differentiating. I know I'm going to need multiple rounds, though, of integration by parts. So this is a great time to use tabular. Not everybody did, but it just makes things a lot easier. So whatever you would have picked u to be is what you're going to put in the first column to differentiate. So x squared minus 6x. And then you're going to integrate or anti-differentiate e to the x, whatever dv was going to be. And then you start over on the left, you keep taking derivatives until you get 0. So this would be 2x minus 6. Take another derivative, 2, and then one more. and then you fill in the column on the right. You keep taking antiderivatives until you have a matching number of entries. So 4 total on both sides, okay? And then the pattern is as follows. When you do tabular, you're gonna multiply on the diagonal from left to right, always. You have 3 products here. The first product, you don't change the sign. Then you change the sign and it alternates, like so. Why is that? Well, if you remember your by parts formula, it's uv minus integral v du. So this minus is going to be here, but then if you have another iteration, when it distributes to the next minus, it's a plus, etc., etc. So that's kind of how it is. It's all these nested negatives getting distributed. And then you just have to remember to add a plus c. So here we go. First product, can you see? It's going to be x squared minus 6x times e to the x. And then I'm going to have minus, who's next? 2x minus 6 times e to the x. So you see, I just added an extra minus very casually. You don't need to like be dramatic about it. And then plus, who's the next product? 2e to the x. And then plus c immediately, because this is an antiderivative. You need to put it now. Okay, let's clean up. I can factor out, do you see e to the x from everybody? So let's do it. And then you have x squared minus 6x minus 2x plus 6 plus 2 plus c. And then you can write everything as e to the x times x squared minus 8x plus 8 plus c. That's it. Good. Okay, next problem. One of my favorites. It's another by parts. So we have integral of cosine inverse of x dx. Ooh, you might say, I only see one term here, and I don't know antiderivative of cosine inverse of x. I know its derivative. Well, whenever that happens, that's what you're going to let be u. So cosine inverse of x, dv is just dx. Because we all just agreed, we know the derivative of this term, but we don't know its antiderivative. Well, that's fine then. Let it be u, because I can find du. Derivative of cosine inverse, it's very similar to derivative of sine inverse, you just have an extra negative. So negative 1 over rad 1 minus x squared dx. Good. And then what's v? Antiderivative of 1 dx, which is just x. Okay, so then now we can rewrite this with our by parts formula. We're going to have u times v. So that would be x cosine inverse of x. Put the x in the front, you know? It looks better. It's more clean. Minus v du. So minus integral. Now you see how we have another minus sign? So I'm actually going to make this plus, okay? And then you have x over rad 1 minus x squared dx. Very good. Okay, how to work with this integral now? I'm looking, I have 1 minus x squared down here under a rad. And then thankfully only x to the first in the numerator. So I can do a substitution. I already used up u though, so we need to do like a t substitution. Let's go ahead, let's let t equal 1 minus x squared, and then dt, perfect, negative 2x dx. So then now I have negative 1/2 dt equals x dx. Fabulous, that's right there. And I can rewrite everything now. Don't forget we still have that cute little x cosine inverse of x up front. Plus integral. X dx is negative 1/2 dt. So dt, I'll put negative 1/2 here over rad t. Good? Okay, let's rewrite it before we integrate so everything's very clear for us. X cosine inverse of x minus 1/2 integral t to the negative 1/2 dt, right? Then you're going to add 1 to the exponent, divide by the new exponent. So if I add 1 to negative 1/2, I'm going to have t to the positive 1/2. Dividing by 1/2 is the same as multiplying by 2 over 1, and then put plus c right away, please. Good, good. These cancel. Then what's next? We just have x, cosine inverse of x minus, that's rad t. Who was t? 1 minus x squared plus c. That one's done. Okay, beautiful. Almost at the end, we just did a little bit of basic trig integrals, not trig sub, but just integration with trigonometric functions, okay? So here we have definite integral, 0 to pi over 2, cosine squared 3x times sine cubed 3x dx. When you have products of sines and cosines, if one of the factors is there an odd number of times, you want to pull it out. Take the odd man out. So I have sine cubed x. I'm going to break that up. Okay, cosine is happy. Leave them alone. I'm going to write this as sine squared 3x times sine 3x dx. Why do we do that? We're getting ourselves ready to do a u sub. So I want sine 3x dx to be absorbed, to all of that to become du. So think backwards. Who would u have to be so that du involves sine? U is going to have to be cosine, and you have to keep the argument the same, 3x. So then check, if you took the derivative of cosine 3x, just don't forget the chain rule. It's negative 3 sine 3x dx, right? You have to multiply by that, 3. Okay, that's perfect. So negative 1/3 du is sine 3x dx, and u is cosine 3x. Don't ever put the exponent on it. This is just going to be u squared. Shoot, what do I do with this? You use your Pythagorean identity. Ah, okay, that's why you want it to stay even. So 0 to pi over 2, I'm going to rewrite everything first. Sine squared 3x is 1 minus cosine squared 3x, and then I still have this sine 3x dx. So now we're ready to go ahead and do our u sub. Oh, but let's get our new limits of integration while we're at it. So 0 to pi over 2, I'm going to plug those in for x. U of 0 is cosine of 3 times 0, which is still 0. Cosine of 0 is 1. And then u of pi over 2 is cosine of 3 times pi over 2. What's cosine of 3 pi over 2? Yeah, it's 0. Good. 270. Okay, so my new integral, let's see. Lower limit's 1, upper limit's 0. Cosine squared 3x is going to be u squared. Very good. This is going to give me 1 minus u squared. And then sine 3x dx is negative 1/3 du. So I'm going to put du here and negative 1/3 out front. Looks pretty clean now, huh? Okay, right away you should have this inclination to flip these limits and then get rid of the minus sign. Anytime you flip the limits of integration, it changes the sign of your integral. Well, how fabulous. Now it's positive. Now we're going 0 to 1. Everybody's happy. I have a student, she gets so angry when the lower limit's bigger. Sometimes it happens. I think it's so sweet. Okay, then this, let's just distribute u squared minus u to the 4th du. Good. I think we're ready to go from here. Anti-differentiating, we're going to have 1/3 u cubed minus 1/5 u to the 5th. Evaluate it from 0 to 1. Such nice limits. So what is this? Just 1/3 times 1/3 minus 1/5 minus 0. What's 1/3 minus 1/5? 5 minus 3 over 15. So 2 over 15. So I have 1/3 times 2 over 15. That's 2 over 45. Good. One last problem. Can't ignore good old tangent and secant now, can we? Okay, so we have indefinite integral tangent to the 4th x times secant to the 6th x dx. So let's see. We have two options. Either u is going to be tangent of x or u is going to be secant of x. If u is tangent of x, du is secant squared x dx. Would that work? So this would be u to the fourth. Can I get secant squared x out of here? Well, this is secant to the fourth x times secant squared x dx. And then, yeah, I can rewrite secant to the fourth x in terms of tangents. So it's looking like this is viable. Is this also an option? If u is secant x, sometimes both work. Du would be secant x tan x dx. So let me see. If u is secant x, I'd have u to the sixth. Can I not use all of them? Let's see. What if I wrote this as tangent cubed x, and then I'm going to take away one of these, secant to the fifth x. That way I have secant x tan x dx. So this would be my du. This would be u to the fifth, but you see how you're stuck now? Why do I say you're stuck? Because tangent cubed, it's not even, so I can't switch it to secants. Right? You can only switch it if it was like tangent squared or tangent to the fourth or tangent to the sixth. So that option does not work. Sometimes both work. Nope. Nope. We have to let u be tangent x. Okay. So now let's rewrite everybody. This is, again, tangent to the fourth x. And then we have secant to the fourth x times secant squared x dx. Now this is all going to be my du. This is going to be u to the fourth. What the heck do I do with secant to the fourth x? Well, remember, secant to the fourth x, that's secant squared x squared. And secant squared x is tangent squared x plus 1. And then that's all squared. So this is u. So this is going to become u squared plus 1 squared, like that. Okay, let's hop to it then. Integral u to the fourth, u squared plus 1 squared du. And then you just got to FOIL this out. Keep the u to the fourth outside first, okay? So when you square this all, you'll have u to the fourth. Don't forget your middle term, plus 2u squared plus 1 du. And then distribute the u to the fourth now. So u to the eighth plus 2u to the sixth plus u to the fourth du. And then we're ready. Take the antiderivative. 1/9 u to the ninth plus 2/7 u to the seventh plus 1/5 u to the fifth plus c. And then go back. Who was u? You're like, I forgot. It's been so long. U was tan x. So plop it back in, and then we're done. 1/9 tan, usually we put the 9 here, so you don't have to do parentheses, plus 2/7 tangent of x to the 7th, plus 1/5 tangent of x to the 5th, plus c. Et voila, that was the exam. Okay, they had 2.5 hours to do it. And for the most part, they were all excellent. So I'm very proud, but always things to improve on. Thought this would be helpful for my class as well as whoever else might be out there working on Calc 2 topics. If you liked this video, if you want to see me solving more exams, just let me know. I have so many. Whatever makes you people happy, what's helpful, I'm here to support you all. Give the video a thumbs up, subscribe if you haven't already, leave me a comment down below. Which was the spiciest problem on the test? Which one do you think was the most difficult? It depended. Like some that I thought everyone would get right, they didn't. And then others that I thought were hard, they did great. So you never know. You can also follow me on Instagram and TikTok, Math with Professor V. And I'll be back soon. Love you all. Bye.